Hello everyone, I am Dante Niewenhuis and today I will be presenting the paper FootPrinter, Quantifying Data Center Carbon Footprint. As we all know, climate change has become a significant problem for society. One big contributor to this is the ICT industry and especially data centers. Data centers have a very large carbon footprint because of the large operations they execute. Sadly, we do not expect this carbon footprint to reduce very soon. With the rise of AI and especially large language models, we actually expect the carbon footprint of data centers to rise. One note we should make at the start is that in this work we have only focused on the operational carbon footprint. This means the carbon that gets emitted during operations and are not emitted, for instance, during transportation of hardware or creating hardware. So why has it been difficult to actually optimize the carbon footprint of data centers? Well, there are multiple issues, but one of them is, for instance, the lack of tooling to actually find out how to optimize, and a lack of guidelines. Another problem is that doing actual experimentation is very difficult, where in other types of research, you might be able to iteratively find out what the best and optimal solution is. In data centers, this is too difficult because it costs a lot of time and it costs a lot of energy plus hardware. This problem is even bigger for smaller operators that often lack insight into the actual workload traces that need to be executed or the actual energy mix that they can get from the providers. There have been some activity though, for instance, especially in what is called power usage effectiveness. Power usage effectiveness is the ratio of the total energy a data center gets and the energy that's actually used by the IT equipment to do the computation. The good thing is that in the last 15 years, we have been able to reduce this significantly. However, we can also see that improvements have been stagnating quite heavily, especially already from 2013. Also, what is not shown in this graph, but is that although we're using the energy maybe more efficiently, the total energy usage is still rising continuously. Again, we do not expect to have any slowdown in this rise. Another big issue with this metric is that it is an incomplete metric for carbon emissions. While, of course, the energy usage overall is important for carbon emissions, it is also very important to look at what the source of the actual energy is. The source of the energy is important to determine what we call the carbon intensity. Carbon intensity is the amount of carbon that actually gets emitted per unit of energy. This means, for instance, that coal will emit more carbon than, for instance, wind. As we can see from the graph to the right, which shows the availability of green and gray energy, and thereby the sort of average carbon intensity of the grid, we can see that this fluctuates very much over time. In this work, we needed to determine a way to determine the carbon intensity of the grid. The energy grid consists of multiple sources of energy, which don't all have the same carbon intensity. To account for this, we did a weighted average, which means how much was available of each energy source and what was their carbon intensity to in that way determine the carbon intensity of the grid. We propose that to properly optimize our carbon footprint, we need a tool that can provide insight directly for data center operators about the carbon footprint of their data center. This can, for instance, help with determining what kind of hardware upgrades we need to buy, what kind of software upgrades we need to buy, or where we should allocate our resources to in research. A tool that we propose as a sort of first step in this direction is the FootPrinter. FootPrinter is a simulation tool that uses event-based data center simulation to determine the carbon footprint of a data center during a workload. A few nice things about FootPrinter is that it works with coarse workloads, so it can be used by most data centers. It provides direct insight into the energy mix, and it thereby helps to provide insight into the impact of different upgrades that a data center can do. To the right, we see the actual sort of setup of a FootPrinter and how we envision a user to use the FootPrinter. So the first step is, of course, gathering data. So this will be done at the data center itself, which of course includes workloads in terms of what's being executed when, the actual hardware setup, so which types of hardware are used, and operational software such as what type of scheduler, allocation policy, etc. are we using. This then needs to convert it into proper input data for the FootPrinter. And this can then be put into the FootPrinter itself. FootPrinter consists of three components. First, we have the simulation component. This is an event-driven simulator named OpenDC, which we develop here at Large Research. And this takes the workload trace and the hardware specifications and replays it. The other part is the energy sampler. This is at the moment based on the NSOE platform, and this allows us to get information of the carbon intensity of the grid during the actual workload. The results from the event-driven simulation and the energy sampler are then combined into what we call the sustainability predictor, which creates the actual output. The output can be divided into two parts. First, we have the performance report, i.e. how fast was it, the quality of service, etc. The second part is the sustainability report. This reports how much energy there was used, what the carbon emission is, etc. From this point, the user can go in two directions. So the first step that we envision is that the user would take the reports and based on this try to update something on their data center. So this would be either going back to the input data, either changing some of the hardware specifications or the operational techniques. This new input would then be used or would then be simulated by FootPrinter to immediately see the impact of the change. We envision that we get a sort of cycle between the input data, FootPrinter, and output, where continuously we can make changes and see what the impact is on the actual performance and sustainability. Finally, if we find a setup that we are very happy with, we go back to the actual data center to apply it in real life. So how does OpenDC, or not OpenDC, FootPrinter work in real life? Well, we will show you two use cases how it can be used. So first, we see just determining what's the carbon footprint of my data center. To do this, we run a workload of 7 days on a specific data center, and we can see 3 results. So first we see graph A, which plots the power draw over time of the data center. Second, in B, we can see the energy carbon intensity that was determined by ENSO-E. Finally, in C, we combine these two to get the actual carbon emissions over this time period. Of course, these are graphs to show you the overtime results. However, these results can also be combined into either numbers or different types of graphs. One thing we can note from these results are immediately that the actual carbon emission seems to have more impact on the actual carbon, or the carbon intensity seems to have more impact on the results than the power draw. A second use case could be the comparison of different locations. Let's say we need to build a new data center and we want to determine what would a good location be. In this case, we run the same workload, but then on 4 different locations. Here we can immediately see how much impact the actual location can make because of the availability of more or less green energy. Of course, we are working with simulation, which means we need to be validating our results. We do this in the following way. We got a data set from Surf-Lisa, which is a Dutch research data center, which provided information about the CPU activity, but also the power draw of the machine. We could use this data to simulate over a span of 7 days and determine how accurate our predictions were. To the right, you see a graph where in the blue, the ground truth is placed, and in the orange, we see the FootPrinter. A very normal or a good way to compare time series data, which this is to use the mean average percentage error. What this means is for each time sample, it determines the absolute or the percentage error, and then at the end takes the average of all these errors. FootPrinter was able to achieve a map or a mean average percentage error of around 3.15%. It is also good to note that in general, FootPrinter is underestimating the power draw rather than overestimating it. In conclusion, we have shown that optimizing carbon footprint for data centers can be very challenging. We propose FootPrinter as a tool that can help data center operators to combat this challenge. We have shown that it can work in several use cases and validated our results. For future, we want to work on expanding our tool. 3 things we want to for sure work on, but are not limited to, are, for instance, thermal and cooling, which is a very important aspect of the energy usage of data centers. We want to look into more complex schedulers, such as load shifting, that can increase or decrease the carbon footprint of a data center. And finally, we also want to include information about embedded carbon. Thank you for listening.